What's up, everybody? Today we are going to be talking about the exciting world of probability. So let's go ahead and jump into this presentation. Probability is the calculated likelihood that a given event will occur. It deals with things like board games or predicting the weather. So there are different methods of determining probability. We have empirical, which is experimental observation, so processes of control. Theoretical, so they use no known elements, so coin tosses or die rolling. Or subjective, so we're using assumptions and we'll say things like, I think that this will happen. In practice, engineers will often blend these approaches. For instance, engineers will assume that each one of the widgets produced at a factory has the same unknown chance of failure, then make observations to determine the likelihood of failure. There are different components to probability. So we have the experiment, an activity with observable results. A sample space, which is a set of all possible outcomes. An event, which is a subset of a sample space. The outcome or sample point, which is the result of an experiment. For example, I might test a brass sample to find its tensile strength, which is the experiment. It might break under any load from 0 to 100 to 1,000 pounds in my tester, or it may not break at all. That would be the sample space. One possible outcome is that a sample could break at 200 pounds. That would be an event. When I perform the test, it breaks at a particular load, which would be the outcome. So as an example, we want to see what is the probability of a tossed coin landing heads up. The experiment is to toss the coin. The sample space, we're going to use a probability tree. And a probability tree lists all the possible outcomes. Many experiments have far too many possible results to write out a probability tree, but flipping a coin once is pretty easy. So we have heads and tails on a probability tree. The event, we get heads, so the outcome is a heads-up coin. Probability is a way of communicating the belief that an event will occur. It's expressed as a number between 0 and 1. We can use fractions, percent, decimals, or odds. So the total probability of all possible events totals 1. We will deal only with probabilities in this lesson. The odds of an event are slightly different than the probabilities, but if you know one, you can know the other. Now let's talk about relative frequency, which is the number of times an event will occur divided by the number of opportunities. So frequency equals n sub x over n, where n sub x is the number of events with an outcome and n is the total number of events. It's expressed as a number between 0 and 1, and the total frequency of all possible events equals 1. So what's the probability of a tossed coin landing heads up? How many desirable outcomes are there? Well, there's one desirable outcome, heads. How many possible outcomes are there? There's 2. So the probability would equal the frequency of x over the frequency of a, or 1 over 2, or 0.5, or 50%. We can calculate the probability of a fair coin flip easily because heads and tails are equally likely. We sometimes call the number of desirable outcomes successes. It's more important to define them as outcomes. For instance, we want to know the probability of catching a cold. We put that in the numerator, but a cold is hardly desirable. So what's the probability of the coin landing tails up? It would also be 50%. We could ask ourselves, what is the probability of tossing a coin twice and it landing heads up both times? So there's our tree. And how many desirable outcomes do we have? Well, we want heads, heads. And that only happens once in our tree. How many possible outcomes are there? There are 4 possible outcomes. So head, 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 tails, tails, head, and tails, tails. And it's important to note here that heads, tails, and tails, heads are different outcomes. So there are 4 possible outcomes. So the probability of heads, heads would be 1/4 or 0.25 or 25%. Next, what is the probability of tossing a coin 3 times and it landing heads up exactly 2 times? So here's our tree. How many desirable outcomes do we have? How many heads, heads do we have? So we have heads, heads, tails, heads, tails, heads, tails, heads, heads. So there are 3 desirable outcomes. And there are 8 possible outcomes. So the probability of landing heads exactly 2 times is 3/8 or 0.375 or 37.5%. A binomial process is when each trial has only 2 possible outcomes, yes or no, on or off, right or wrong. Trial outcomes are independent, so tossing a coin does not affect future tosses. The probability of heads occurring on subsequent coin flips doesn't change. A binomial process doesn't have to be a 50-50 chance. Getting a 6 on a dice roll is also binomial. You either get the 6 or you don't, even though the odds are 1 in 6. Next, let's talk about the Bernoulli process, which is just a series of independent trials. The formula here is for a binomial process, combining the results of n independent Bernoulli trials. So let's define some variables. So P is probability, X is the number of times for a specific outcome within n trials. N is the number of trials. Little p is the probability of success on a single trial. Q is the probability of failure on a single trial. And the exclamation point is the factorial, which is the product of all the integers less than or equal to that number. So if we had 5 factorial, it would be 5 times 4 times 3 times 2 times 1, which would equal 120. All of this equals n choose x, which is the number of distinct groups of x things that can be chosen from n distinct things. It's a combination. Most scientific and graphing calculators have a factorial key and an n choose x key. Both functions can be found in the probability menu on most graphing calculators. So we want to know, what is the probability of tossing a coin 3 times and it landing heads up 2 times? We can use the binomial formula, and if you see here, they just put everything in the numerator altogether, whereas on the previous slide it was separated out. So the probability of tossing a coin 3 times and it landing heads up 2 times, we have n factorial, which in this case n is 3. So we would have 3 times 2 times 1, times p to the x power, where p is the probability of landing heads, so that would be 0.5. X is the number of times we want that to happen, which is 2. We have q, which is the failure rate, or 0.5, to the n minus x power, so that'd be 3 minus 2, or 1, divided by x factorial, so 2 times 1, times n minus x factorial, so 1 times 1. This gives us a probability of it landing heads up twice when we flip a coin 3 times at 37.5%, or 0.375. The law of large numbers tells us that the more trials that are conducted, the more likely the result becomes closer to the theoretical probability. So for trial 1, if we toss a single coin 5 times, we could get heads, tails, heads, heads, tails, which would give us a probability of 60%. But if we tossed the same coin 500 times, we would get something maybe closer to 50.2%, which is really close to the theoretical probability of 50%. It's still possible to flip a fair coin many times in a row and get significantly different numbers of heads and tails, but this is very unlikely. So there's some key words that we need to know when we're talking about probability. The word "and" means multiplication. So independent events occurring simultaneously, product of individual probabilities. If events A and B are independent, then the probability of A and B occurring is P of A and B, or the probability of A times the probability of B. So what's the probability of rolling a 4 on a single die? So we have 1 desirable outcome, 6 possible outcomes. So the probability of rolling a 4 is 1/6. What's the probability of rolling a 1 on a single die? Same thing as rolling a 6, it would be 1/6. What's the probability of rolling a 4 and then a 1 in sequential rolls? Well, that would be probability of 4 times the probability of 1, which would be 1/6 times 1/6, or 1/36. We can multiply these probabilities because they are independent of each other. Or means addition. Independent events occurring individually, it's the sum of individual probabilities. If events A and B are mutually exclusive, then the probability of A or B occurring is probability of A plus the probability of B. If A and B are mutually exclusive, it's not possible for both to occur at the same time. For example, you might want to know the probability of drawing either one of the 2 cards, a 2 of diamonds or a 2 of spades, from a single draw. So what's the probability of rolling a 4 on a single die? Again, it's 1/6. Probability of rolling a 1 on a single die, also 1/6. What's the probability of rolling 4 on a single die, or a 1 on a single die? So that'd be probability of 4 plus the probability of 1. So 1/6 plus 1/6, or 2/6, which is 33%. The word "not" means an independent event not occurring. So it's 1 minus the probability of occurrence. So what's the probability of not rolling a die, 1 on a die? Well, it'll be probability equals 1 minus the probability of 1. So 1 minus 1/6, or 5/6, or 83%. So let's do an example. 2 cards are dealt from a shuffled deck. What is the probability that the first card is an ace and the second card is a face card or a 10? How many cards are in a deck? There are 52. How many aces are in a deck? There are 4. How many face cards are in a deck? 12. And there are 4 10s. Dice rolls and coin flips are classic examples of independent events. Drawing cards is a classic example of a set of dependent events. So that's why we're using cards right now. What's the probability that the first card is an ace? So that'd be 4/52, or 1/13, or 7.69%. Since the first card was not a face, what is the probability that the second card is a face card? It will be 12 over 51. We have 51 as our denominator now because we eliminated the first card, which was the ace. So 4/17 is 23.53%. Since the first card was not a 10, what is the probability that the second card is a 10? 4/51, or 7.84%. Going back to our question, 2 cards are dealt from a shuffled deck. What is the probability that the first card is an ace and the second card is a face card or a 10? We would get this equation. So the probability of an ace times the quantity, the probability of a face card, plus the probability of a 10. So 4/52 times 12/51 plus 4/51, which would give us 2.4%. And if the first card is an ace, what's the probability that the second card is a face card or a 10? Now, this is a different question than the one up here. This was the combination. This was an and statement of what's the probability that the first card is an ace and the second card is a face card or a 10? This question is asking us, if we eliminate the ace from the deck, what's the probability that the second card is a face card or a 10? It's just the 16/51 fraction, or 31.37%. Conditional probability is the probability of event E given event A. So for example, 1 card is drawn from a shuffled deck. The probability that it is a queen is 1/13. However, if we already know it's a face card, the probability that it's a queen knowing that it's a face card is 4/12, or 1/3. The probability of 2 events, A and B, both occurring, we would take the probability of A knowing B times the probability of B, which equals the probability of B knowing A, times the probability of A. If A and B are independent, then the probability of A and B equals the probability of A times the probability of Bayes' theorem says that Bayes' theorem calculates a conditional probability based on all the ways the condition might have occurred. The probability of A, given we already know the condition E, is given by this formula here. Bayes' theorem is intuitive for most people, but computing it can be very difficult. So let's go ahead and look at an example using LCD screen components for a very large cell phone manufacturing company that are outsourced to 3 different vendors. Vendors A, B, and C supply 60%, 30%, and 10% of the required LCD screen components. Quality control experts have determined that 0.7% of vendor A, 1.4% of vendor B, and 1.9% of vendor C components are defective. If a cell phone was chosen at random and the LCD screen was determined to be defective, what is the probability that the LCD screen was produced by vendor A? Note that the vendors are mutually exclusive. Any given screen is outsourced to only one company. So the notation that we're going to use is that big P is the probability, D equals defective, A, B, and C are going to denote the vendors. The unknown to be calculated is the probability the screen is from A, given that it is defective. So we know some different probabilities. We know the probability the screen is from A is 60%. We know that the probability the screen is from B is 30%. And we know that the probability the screen is from C is 10%. We know some conditional probabilities. So we know that the probability that the screen is defective, given that it's from A, is 0.7%. The probability that it is defective, given that it's from B, is 1.4%. And the probability that it's defective, given that it's from C, is 1.9%. I don't know why we would use manufacturer C if we know that A has such low probabilities of defect, but that's our example. Anyways, we could use Bayes' theorem. So the probability that the screen is defective and from A, we have up on the top. The probability that the screen is defective from anywhere is there on the bottom. So the probability that the phone is from manufacturer A, given that it's defective, we can plug in our known probabilities and calculate that the probability of that happening is 40.7%. Hopefully you found this lecture informative, and I'll see you next time.